Okay, so now that we've talked about discrete probability distributions and we have a good handle on the rules of probability, we're going to go ahead and continue with our discussion of discrete probabilities with a particular discrete probability, which is called a binomial probability distribution. Now, there's certain criteria that makes a probability experiment a binomial distribution, and we'll talk about that in just a bit. But before we continue with this section, I want to start off with a preview example here, okay, to kind of motivate this whole section. All right, so this first example has to do with, well, we toss 4 die and count the number of times that 3 appears. Okay. Now, of course, a die has 6 sides, and a 3 is one of those particular sides. Okay. So let x represent the possible number of counts of 3 appearing. Okay. So we toss it 4 times, and we're just counting the number of times that we see a 3 appear. Okay. Construct a probability distribution for x. Note the probability of 3 appearing in any one of the dice is 1 out of 6, of course, because there's only one 3 out of 6 sides. Okay, so we're going to say that if 3 appears, we say that yes, 3 appeared, and we're just going to give that the letter y, and then we can say that the probability that yes, 3 appears is 1 in 6. And if 3 does not appear, well, it's just anything other than a 3, so we say no, 3 did not appear. So the probability that 3 does not appear is, well, the other 5 sides, right? So these are essentially complements of each other. A 3 appears or it doesn't appear. Even though there's 6 sides, 6 possible outcomes per die, we forced it to be 2 outcomes. We said 3 appears or 3 does not appear. Okay. So again, x represents the number of possible counts of 3 appearing, right? Well, in 4 die, how many times can 3 appear? Well, it can appear 0 times. That means the 4 die were anything other than a 3. Okay, so we would just say that that was a 3 did not appear 4 times. No, 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 no. Okay. What's the way that a 3 could appear once? Well, it could appear on the first die and not on the other 3. Or it could appear on the second die and not on the other 3. So it would be no, yes, no, no. Same thing for the third and the fourth. So there's 4 ways that 1 3 can appear. Okay. Now, how many ways can 2 3s appear? How many y's can 2 y's out of 4? Well, we have the first 2, right? You can have the first and the third, or the first and the fourth. Okay, so the first and the second, first and the third, first and the fourth. And then we can also do, well, let's do second and the third. Oops. The second and the third. And then we can do the second and the fourth. And then finally, the third and the fourth. So that should be all the possible ways that we can get 2 3s out of 4 die. Okay. All right, now how many ways can we get 3 of them that are yes and 1 no? Well, the first 3 can be yes. Or the first 2 and the last one can be yes and the third one's a no. So what we're going to do is this n is just going to move towards the left every time we repeat this. And then the no can be on the second one. And then it could be no 3 on the first one, and then a 3 on the last 3 die. Okay, so this is it seems to be kind of rare of an occurrence that you get 3 3s out of 4 die. And we'll see. We'll talk about what the probability of that is on the next column here. And then finally, how many ways can you get all 4 die to be a 3? Well, there's really only one way that they're all 3s. Okay, so you can kind of see that it's kind of looking like a bell shape, right, in terms of the number of ways that this can happen. Okay. All right, so how do you come up with the probability of this? Well, would you agree that each die is independent from each other, right? And if we're saying that, let's see this first example, the probability that 3 does not appear on each die, they're independent, right? So if it's no and no and no and no, then the probability that a no and a no and a no and a no, and these are all independent events, would simply be the product of each individual probability. So for example, what's the probability of not getting a 3? Well, we know it's 5 out of 6. For each one of these. So there's 4 of them. Okay. If it's the same factor rate multiplied 4 times, then we can also write that as 5, 6 to the what power? Well, 4. Okay. And if we get some sort of decimal equivalent for that, let me go ahead and round to just 4 decimal places. I get something approximately 0.4823. So it's about a 48% chance that you won't get a 3 in 4 rolls of a die. All right. Well, how many ways can you get? Well, you can get it a 1 3. Okay. So you can get it this way. You can get it this way, or this way, or this way. So these are considered OR probabilities, right? It could happen this way, or this way, or this way, or this way. So if we just focus on one of these, well, 1y, the probability of getting yes is 1/6. Right? And then there's 3 no's, and the probability of no is 5/6. Aren't these factors all going to be exactly the same since there's 3 no's and a y? So if this or this or this can happen, we would just be adding them across, which is also the same thing as just 4 times that. Okay? So this comes out to be 4 times, we have 1/6, and then we have 5/6, but to the 3rd power. What you notice here is that the powers on both of these factors add up to 4 each time. So there's 4, 1 plus 3 is 4, and you'll see that same pattern as we continue. Again, this will be approximately 0.3858. 0.3858. Okay. Now here we have 6 terms of the same 2 y's and 2 n's. So we have 6. The y's are 1/6, 1/6. And the n's are 5/6, 5/6. So we have 6, 1/6 squared, 5/6 also squared. Again, 2 plus 2 is 4. And if you were to multiply this out, you would actually get 0.1157. So if just adding up these 3, so far we have 48 plus 38, which is what, 86, I believe, plus another 11. That's about 95%. So far we have about 95% of here. And of course, these all have to add up to 1. So these last 2 should be very small in terms of the probability of these occurring. Okay, so let's see. What do we get here? Well, we have 3 y's and a no, right? And this is repeated 4 times, right? So we have 3 y's. That's a 1/6, 1/6, 1/6, and a no. Again, it'll be 4 times 1/6 to the 3rd, 5/6 to the essentially 1 power. And of course, if we multiply this out and round to the nearest 10,000ths place, right, 4 decimals, 0.0154. 0.0154. Okay, and then finally the last one, y. That's just going to be 1/6. There's only one term of this, 1/6, 1/6, and 1/6, which is 1/6 to the 4th power. Now I do want to kind of pause here and just introduce you to scientific notation, really. Let's go ahead and switch over to the calculator here. Okay, now I did want to show you how to actually put this into your calculator. So if you were to put, let's say, parentheses 1 divided by 6 divided by, 1 divided by 6 parentheses, and then raise that to the 4th power. Now, you'll notice something that's going to be a little weird here. Okay? If you press enter, what do we get? We get something that starts with a 7 point whatever. Again, we're talking about probabilities here, right? Can a probability be anything other outside of the range of 0 through 1? No. So why do we have a whole number here? Well, this is actually written in scientific notation, right? It's 7.716 and so forth. This little e just means times 10, and this -4 means to that power. So if I were to go over to the sheet here, back to the notes, I'll just do, I don't know, like 3 decimal places, 7.716. 7.716 times 10 to the -4. That's what we have there. Okay. Again, this is in scientific notation. We're going to have to move this decimal place 4 times to the left because this is technically a small number. 1, 2, 3, 4. That's our new decimal place. And we're going to go ahead and put zeros in between. All right, so if we were to round this number to the closest, to 4 decimal places, well, we look at this 4th decimal place, which is the 7. Look to the right. If it's a 5 or greater, then it moves up. If it's not, then it stays the same. In this case, it's a 7, so it does move up. So we get 0.0008. That's how you get that last one. 0.0008. Okay, so again, it's in the 4th decimal place, which is the 10,000th place. So if you were to repeatedly toss 4 die 10,000 times, you would expect to get all 3s only 8 out of those 10,000 times. So 8 10,000ths. That's how you interpret that. And of course, these should all add up to be 1. All right, so let's go on to this section. And I'm going to keep on referring to this example as we start developing our understanding of a binomial experiment. All right, so the objectives here are to determine whether a probability experiment is in fact a binomial. There are certain criteria that it has to meet. We're going to compute binomial probabilities of binomial experiments. We're going to also compute the mean and standard deviation of a binomial experiment. This turns out to be very easy. If you identify something as a binomial, calculating the mean and the standard deviation is a very easy process, as we'll see. Okay. Otherwise, we would have to use the old-fashioned mean, which is the sum of x times probability of x, which could be tedious. But again, if we know something's binomial, this process it's actually a very quick process. And then construct binomial probability histograms. Okay, so determine a probability experiment is a binomial experiment. All right, so there's 4 criteria. Okay. So there's 4 criteria for the binomial experiment, and we're going to kind of do problems where we have to ask ourselves, does it meet this criteria? Quite often that you might actually just commit these to memory. Okay. So a binomial experiment is an experiment with the following characteristics. Okay. Experiment is performed a fixed number of times. Each repetition of the experiment is called a trial. Okay. And we denote the number of trials with the letter N. Each trial has 2 disjoint possible outcomes, either a success or a failure. Each trial is independent from each other. Again, for things to be independent, it just means the outcome of one trial does not affect the outcome of another trial. And then the probability of success is the same for each trial. Okay. So if we look at our previous example, does it meet this criteria? So we're rolling a die 4 times, correct? Okay. So that in our case, that would be n equals 4. All right. A fixed number of times. And in our case, was there two disjoint possible outcomes, success or failure? Yeah, we can successfully get a 3 or not a 3, right? We forced it to be two outcomes here. Were the trials independent? Well, for a die, every time we roll the die, the outcome of one of those dice shouldn't affect the outcome of another die. So yeah, these are independent trials. And does the probability of success remain the same in each trial? Well, again, what was the probability of success? Well, rolling a die was a 1 in 6 chance. I'm sorry, rolling a 3 in a die was a 1 in 6 chance. And from die to die, that 1 in 6 did not change. It was exactly the same. So yeah, what we had before was a binomial, according to these criteria. Now, it has to meet all 4 criteria. If it doesn't meet all 4 criteria, then it's not binomial. Okay? It can meet 3 of them and not 1. It won't be binomial. Again, the number of trials is represented by lowercase n. Probability of success in one trial is represented by p. The probability of failure would be represented by 1 minus p. Sometimes this is known as q. Some textbooks use q for that, but it's related to p. It's just the complement of p. And x denotes the number of successes in n trials, and those always range from 0 on to n. If it meets these 4 criteria, then x is called a binomial random variable. And we say x is distributed as a binomial random variable with n and p, where these two values don't change throughout the problem. Okay, n and p stay fixed. Determine which of the following probability experiments qualify as a binomial experiment. All right, so we have a few examples here, and we just have to go down the criteria and ask ourselves, well, does it meet each one of these criteria? All right, so let's start with the first example here. It says, a basketball player is asked to shoot 4 free throws. The number of baskets he makes is recorded. All right. First of all, first criteria is, do we have a fixed number of trials? Question mark. And what would those trials be? Well, in this case, we asked this basketball player to shoot 4 free throws, right? Right? So we're given 4 trials, right? 4 attempts. So yes. And in this case, n is equal to 4. 2. Are there 2 outcomes? Well, he can either make it or not make it, right? So yes. Make or not make. All right, so far so good. We have 2 yeses. We just need 2 more. 3. Do we have independent trials? Again, a trial is considered every shot attempt here. All right. Well, the argument can be made that maybe these shots do depend on each other. I know that if I were to shoot a basket, I would shoot first, and if I miss, then I would adjust my shot based on the previous shot, right? So that can be an argument that they're not independent, that they depend on each other. But let's just say that there's nothing that really indicates that in this problem. We can probably say that this person has probably been warmed up, and every shot seems to be independent from each other. Okay, so an argument can be made that these are independent trials but unless there was a specific indication in the problem that would lead you to believe that they're dependent on each other, then I would assume that they're independent. So let's just go ahead and say yes, they are independent trials. And then 4, what do we have here? Well, again, we have to ask ourselves, does the probability of success in each trial remain the same? All right. So now it doesn't tell us a particular probability of this person making the shot, but we can just make one up. For example, let's say this person makes 75% of all his free throws, right? The simple fact that we are dealing with the same person in each one of the trials would lead me to believe that, yeah, this person inherently has a certain percentage of shots that he makes, right? Therefore, the probability of success is the same in each shot. Now, if there were 4 different people, I would say no. There's different skill levels, right? So the probability of each person making the shot might be one person 50%, one person 75%, one person 0. But since it's the same person, I would say, yeah, the probability of success is the same in each trial. So I would say yes. I would say same person. Okay. We have 4 yeses. Again, that third one is probably questionable, but nonetheless, we do have 4 yeses. So in this case, we can say that, well, we can define X to be the number of shots made out of 4. Okay, we're clearly defining, we're going to define a random variable. Okay, X is the number of shots made out of 4, so it can range from 0. He can miss all 4 shots. 1 shot, 2 shots, 3 shots, 4 shots. You can't make any more than 4 shots out of 4, right? And so we have 4 yeses, so we can say that X is distributed as a binomial, where N is the number of trials. In our case, it's 4 shots. And P, it wasn't specifically told to us, but if they did tell us it would be some sort of number. I'll just put some number here. Okay, so that's what that is. So you always want to define what your X is and then state what the N and the P are. Okay, just like that. All right, so right now we're not really doing any problems. We're just identifying whether a probability experiment that we're being asked to evaluate is a binomial. Okay, again, why are we interested in what it's a binomial? Because a binomial is a very well-defined probability distribution. And if we do identify something as binomial, there's a lot of nice properties about the binomial, which we will see. Okay. A poll of 1,200 or 1,200 registered voters is conducted in which the respondents are asked to answer yes or no on whether they feel that Congress should reform Social Security. Assumed probability of someone voting yes is 30%. Okay. So again, do we have a fixed number of trials? Fixed number of trials. Okay, in the previous problem, it was shots taken, right? What would be the trials in this case? Well, they're polling 1,200 registered voters, and they're asked to answer yes or no, right? So in this case, what we would consider a trial is every single voter that they go up to, okay? Because they go to a voter and say, well, do you think Social Security should be reformed? Yes or no, right? And they go on to another person, yes or no, right? So each person is considered a trial. So I would say yes. N equals 1,200 in this case, okay? Do we have 2 outcomes per trial? Well, yeah. They could either respond yes or no to the question. Now, do we have independent trials? Okay. A poll of 1,200 registered voters is conducted in which the respondents are asked yes or no. Now, again, there could be some arguments made that they are not independent, that they might be dependent. As long as you poll correctly, which means You randomly select people. Okay, you probably wouldn't do on the street polling, especially in groups, because people in groups tend to agree with each other. Maybe even if they don't actually have the same opinion, they might agree with each other, right? So one person's response might actually be dependent on another person's response. But there was nothing in this problem that indicated that we had that type of case. And polls typically do use random sampling. So I'm going to go ahead and say just yes here. And of course, the last one is the probability of success the same in each trial. And what do they mean by success? Well, they're saying the probability of somebody voting yes is 30%, right? How do they know that? That usually comes probably from a prior study, okay? So in this case, it's saying yes. The probability that someone will respond yes to this survey is a 30% chance. Why would, if they already know what the probability is, then why would they continue to do polls? Well, public opinion does change over time, so they always try to create new updated polls, right? To update those statistics. Okay, so yeah. In this case, the probability of success, and we're essentially assuming success is voting yes, is 30%. Okay, again, we have 4 yeses. So let's define our random variable here. X is going to be we're interested, they give us the probability for somebody voting yes. So let's go with that. The number of yes responses out of 1,200. And these yes responses can be from 0 all the way up to 1,200, right? X can range anywhere between there. Okay. X is a binomial where n is, in this case, 1,200. And the probability of success in any one of the trials is 0.30 or 30%. All right. So far we've had 2 binomials, and we only have 1 problem left. Okay. So take a lucky guess if this is going to be binomial or not. Well, let's see. Because not every probability experiment should be binomial, right? So let me kind of show you what we have here. All right, so 3 cards drawn from a deck of cards without replacement, and the number of aces is recorded. Do we have a fixed number of trials? Okay. They're saying that 3 cards are drawn from a deck of cards without replacement, and the number of aces is recorded. Well, yeah, they're drawing 3 cards from the deck, right? 2, do we have 2 outcomes? Well, what are they looking for here? Well, they're recording the number of aces, right? So they're essentially saying it's either an ace or not an ace, right? So again, yeah, they forced it to be 2 outcomes. Yeah, of course, there's 52 cards, and they all have different characteristics. But in this case, they're only really interested in whether it's an ace or not an ace. Okay, so there's still 2 outcomes. 3, do we have independent trials? Again, the definition of independent is that the probability of one event isn't influenced or isn't affected by the result of a prior event. Okay. 3 cards are drawn from the deck without replacement. Okay, so again, if you have a standard deck of 52 cards, right, and you pull a card out, if you don't replace that card back into the deck, you no longer have 52 cards in that deck for the second succession, right? You have 51. And then again, on the 3rd card, you'll have only 50, right? So you see how each trial does depend on the outcome of the previous trial? So, no. It's because of that word, without replacement. Without replacement. So we have one no, so it's already not a binomial. We can go with the fourth one just to be complete here. The probability of success is the same in each trial. Again, the probability of success in the first one was what? There's only 4 aces out of 52 cards. In the second trial, it would change, right? Because it wouldn't be out of 52 cards anymore. So it would change. So again, no. P changes each trial. It would also change whether you got an ace or not in the first trial, right? So, again, so in this case, not a binomial experiment. Now, again, why are we so interested in coming up with the binomial experiment? I probably should have mentioned this when we were doing that preview example. Because wasn't it very tedious to come up with all those probabilities? Let's go back up to that. Wasn't it really, really tedious to come up with all those probabilities here? You see that? And if we know something's binomial, these probabilities are very, very easy to find, which we'll see. Because if it's binomial, and it's a very well understood distribution, then there's usually a formula that will very easily get these probabilities for you. If it's not a binomial, or it doesn't have any, it's not one of those very well understood distributions, then you have to do this manually every single time. So for that problem that we just did with the ace chosen without replacement, again, that would have to be done manually, which could be kind of hard to do, especially if we're using conditional probabilities